Hello, everyone. All right, so we just did a graded, not really graded, it was like practice FRQ on accumulation. So we're going to continue to do accumulation type stuff and build on that. But today there's one kind of easy topic. This should be a pretty fast lesson on finding something called the average value of a function. So this is typically a topic found when you're doing accumulation because it involves accumulation. So real quick, example, I'm actually going to call this a lead-in example. Lead-in example. Okay, if I gave you the following numbers, 2, 5, 8, 11, 6, I can ask you to find the average of these numbers. How do you find the average? You add them all up. So 2 plus 5 plus 8 plus 11 plus 6. And you divide by the number of numbers. So 1, 2, 3, 4, 5. There's 5 of them. So this would be 2 plus 5 is 7, 15, 21, 32. 32 over 5, which is 6 point something. Whatever, it's about 6. 6.2 or something. Okay, so that's the average number. What does an average number mean? It means, well, you have obviously some numbers that are less than it and some numbers that are greater than it. And this one's actually pretty close to it. It's like the average number. So you all know what an average is. In statistics, you find averages a lot more. But it's kind of like the middle. It's one way to talk about the middle value is the average, otherwise known as the mean. All right, so using this same logic of kind of thinking of like the middle number, I can find something called the average value of a function. So if I gave you this function, and I gave you this interval, I could ask you to find like the average y value. Like, what is the average y value? One way to do that would be to say, okay, well, maybe if I find f of 1, f of 2, f of 3, f of 4, and f of 5, and divide that by, like, add those numbers up, and divide by the fact that I'm dealing with 5 numbers here. Maybe that's one way. So plug 1 in, you get 1 plus 4 plus 9 plus 16 plus 25, and divide by 5. That's one way. That kind of feels like a Riemann sum a little bit. And yes, I mean, that's why it's dealing with accumulation. This number would be 10, 14, 30, 55 divided by 5, so 11. So that's kind of like you're telling me the average y value is 11. But this approximation isn't super accurate, because think of it this way. As x squared grows, the y values get bigger and bigger faster. So really, you're giving like the same weight to 1 and 25, even though this thing grows bigger, like faster, because it's increasing at an increasing rate. It's concave up. So is there a better way to actually find the average y value? Well, you could always just try including more. Maybe you could do like 10 of the y coordinates, but then what's to stop you there? Why couldn't you just do 100 of the y coordinates? So instead, hopefully you're kind of thinking, well, rather than do a kind of statistical approach where we add and divide by the total, what if we take the integral, or the area under the curve, or the accumulation from 1 to 5, and then divide that by, and then here's how we divide it, ready? We divide it by the length of the interval. So 5 minus 1, the length of the interval. So basically your endpoint minus your start point, length of interval. So what does this calculation give us? Well, I have you do this by hand, I think, on the homework, because don't forget, at the end of the day too, yes, we still have to be able to, Desmos. Oh, there it is. We still have to be able to find antiderivatives by hand. We've been getting a little privileged with the whole int in Desmos, and we'll continue to be privileged. So we could do int 1 to 5, no, 1 to 5 x squared dx, and then divide that whole thing, nope. Take that value, divide that by 4, and 10.33. So actually I was a little wrong on my previous assessment. Because we had more of the lower values at the bottom, we weren't including as many, but we could see that the real answer for this interval from 1 to 5, the actual average value is 10 1/3, 10.33. That's like your average y coordinate in the interval. It's called the average value. Average value. Okay. So it's really all it is. So here's the formula. I'm just going to give you the flat out formula. We'll do one more example and then a table example and be done. Formula says to find the average value of f of x, so some function, over the interval a to b, that is just the accumulation from a to b of the function, then divided by b minus a, or times 1 over b minus a. That's typically how you see it. 1 over b minus, it's the same thing. So dividing by 4 is the same as multiplying by 1/4, which I'll show you in the next example. All right, so let's do another example. If I have f of x equals, the formula right there, square root 2x minus 1. I want to find the average value of f of x over the interval. Let's go 2 to 7. Well, pretty straightforward. It's the accumulation from 2 to 7 of this radical 2x minus 1 dx. And we're accumulating, we're getting an accumulation total, but then we're bringing it back to an average by multiplying by 1 over 7 minus 2. So somebody's asking, a couple people have actually asked me, is there, like we accumulate under a rate to get a total. What happens if you accumulate under a total? Does that give you anything? Yes and no. Not really in terms of a value, but when you put this thing in front, this divided by, when you're dividing by the interval length, it does give you the average value. So this is one case where, yes, you are going to accumulate the actual function. And then when you divide by this piece in front, you're getting back to an average value. So then we can do what we just did. Let Desmos do the work for us. This is one you should be able to do by hand. But again, we will let Desmos be our guide, or soon to be graphing calculators be our guide. 2 to 7, and then divided by 7 minus 2, which is 5. So 2.77. Does that answer make sense? That means, does this answer fall between all of the y values that are actually in this graph of this function? Let's see. So yeah, the y values range from like 0-ish, well, starting at 2, it's a little bit bigger, from like 1.7 up to like 3.6. So yeah, that seems like a middle value. That is the average value of this function over the interval. This calculation is going to come up a lot in free responses soon. And then, just like I said before, rather than divide by 5, that's the same as multiplying by 1/5. Same answer. So that's why we typically see it this way. It's a little bit cleaner than dividing a whole integral expression by 5. All right, so the last example. And by the way, on the discussion, I ask you, on the homework, I actually ask you to do this. You are finding average value, not to be confused by average rate of change. Average rate of change is our normal average rate of change where you do f of b minus f of a over b minus a. That is a different value. I'm asking for the average y coordinate here. Average rate of change would give you the slope between the 2 points. It's how the function's changing on average. So you can see how in an FRQ that can get very confusing. One part they could ask for the average value of a function, and then in the next part they could ask for the average rate of change of the function. Those are two very different things, and I really want you to get the difference between the two on the homework and the discussion. So keep those things different in your mind. Last example, if I give you a table with x and f of x, and I give you these values, 2, 4, 6, 8, 10, and I give you 1, 3, -2, -1, 3. And I ask for a average value. This one would have to be, remember we talked about this, approximation, because all I have is a table. I actually don't have the actual function or graph of f of x over the interval 2, 10. A couple of you have asked me, how do you know which approximation strategy to use, like Riemann sums or trapezoidal? They'll tell you. They'll say using let's do a right hand Riemann sum with 1, 2, 3, 4 subintervals. So the calculation would be 1 over 10 minus 2, accumulation from 2 to 10, area under the curve of our function. This piece we're not going to find exactly, so we're going to approximate it using a Riemann sum, a right-hand Riemann sum. So again, if we do this without the graph, without having to graph it, this distance is 2, we're going right to left. So base length of 2 times the height, which is this value, plus this distance, 2 times this value, plus this distance, 2 times this value, plus this distance, 2, they're all 2, times this value. It's a right-hand Riemann sum. And that would give me 6 minus 2 minus 4 plus 6. So what is that? 12, 10, 6. So 6 times, though, 1/8. And that gives me back to the average value of 3/4. Does 3/4 seem like a logical value? Yeah, because we have a -2 and a -1, and we have some above it. If you got an average value of like 50, and it's bigger than all the values in the table, that you did something wrong. So don't forget to divide by or multiply by this fraction. Okay, divide by the interval length, or multiply by 1 over the interval length. Okay, so that's the idea today. Not too complex, but in class we're also going to be going over the performance task. So short little mini lesson today. Hooray. This one's short. Next one might be a little short too, as we continue to do these accumulation type FRQs together and learn some stuff coming up. All right, that's it.